Okay, so in this one, says we have a function w gives a person's weight t after she begins a diet. Now it doesn't say here, the key is it doesn't say what the weight is in, but since we're in the US, let's call it pounds. Okay, so that's going to be a key thing because they're going to have to figure out what that is. But it's t weeks after she begins the diet. Now we need to write a sentence of interpretation for each of the following statements. All right, well, W0 equals 167 and W12 equals 142. Okay, well, what does W0 mean? Okay, well, at time zero, so basically when she's starting her diet, that first day at time zero, she weighs 167 pounds. Okay, and then after 12 weeks, on the diet, she weighs 142 pounds. Okay. So that's what I would say. And you could say, instead of at time zero, you could say before she begins the diet or at the beginning of the diet. Basically, as long as you're telling us, it's at the very beginning, that's what she weighs, and then after 12 weeks, that's what she weighs. That should work. Okay. All right. So A. So B. W prime of 1 is equal to -2. W prime of 9 is equal to a -1. All right, so what does that mean? Well, here our input is 1, so we know at 1 week. So that's where we're at. So what we can say is after 1 week on the diet. Now, what's happening? What's going on here? Well, we know that that's the person's weight, and what is it doing? Now, this is a derivative, so that's the change. So now, she's decreasing her weight. She started up here, and she's coming down here. So, she's coming down, and we don't know what's going on in between here. We have to kind of think about that because we have to actually sketch this graph. But, it's coming down, and so we're going to have, well, at some point, and that's all above the line, not below there. And we have this tangent line, and that tangent line is equal to a slope of -2. So what we can say is after 1 week on the diet, the person's weight is decreasing, okay, and it's going down by 2 pounds per week, decreasing by 2 pounds per week, okay. Now it's a saying here. Same thing, except it's after 9 weeks, it's decreasing by 1 pound per week. So after 9 weeks on the diet, the person's weight is decreasing by 1 pound per week. Okay. So that's where it's at there. So that's kind of how our slopes are at the 1. So that was at 1 week, 9 weeks. It's going to be, it's gradually, it looks like it's kind of sloping off. It's not going as fast. And so that tangent then would actually be better. So really it's not going as steep at this point. We're going at a slower rate. It's about half of what it is before that. Okay. All right, so C, what does this say? Well, it's taking the derivative again, and it's saying, well, basically, we could rewrite this as W prime of 12 is equal to 0. All right, so after 12 weeks on a diet, the person's weight was not changing. Since we have to say something, was not changing because it was staying constant. Okay, and we have to have that ing in there, so changing is not changing. That's how we're going to get that. Now, after 15 weeks, what is it doing? Well, now it's going back up because we have a positive slope now. So after 15 weeks, and kind of like a diet, you go back up after a while. After 15 weeks on the diet, the person's weight was increasing by 0.25 pounds per week. Okay. And now it says sketch a graph. So we better kind of erase what we have up here and kind of sketch a little bit better graph. That was kind of to get us to understand what was going on. And so we know if we look at our graph, and this isn't going to be perfect here, of course. So we win 1 week, we know at 9 weeks, we know at 12 weeks, and we know at 15 weeks. So we'll assume that those are all about there. So here we're at 167, and then we're going to hit this thing here, and that's going to be at 12 weeks, we're at 142. And so how are we going to draw it? We're going to draw it so it's going to be decreasing, and I'm not going to get this right because I'm not going to get a good curvature on here. So it's kind of steeper now, and then I've gone too far, so we got to start over again. All right, so let's try this again. Where did my pen go? So it's going to kind of come down. Well, that's too shallow. Again, I am not the best drawer on the computer or in person, so. All right, so maybe let's go backwards. So we know at week 15 we're going up, and we're going to plateau here, and we're going to start going up, and then we're going to go higher until we kind of something like that. So this is kind of the curve down. We're not getting that good vary there, but it's curved down at this spot, and then it's starting to curve back up here again. So kind of that's like that. So again, not the best in the world. Maybe if we could increase our size of our marker, that would look little bit better. But that's kind of what it is. It kind of comes down, and then it's going to go back up again. And so that's kind of the direction our graph should look. Okay. All right, so what about doubling time? What does this one say? It says the function d gives the time in years that it takes an investment to double if interest is compounded continuously at r%. So we're going to have r%. So it's going to be d of r, it looks like. Okay. So what are the units on d prime of 9? All right. Well, what are our output units? Well, our output units are going to be basically years, the time it takes to double. So that's going to be years. And what is the denominator? What's the input? Well, we're inputting the rate. So it's going to be years per percent. Maybe it's percentage point because it's going to be percentage piece, and so we'll just have one single point, and so it's going to be years per percentage or percentage point, however you want to look at it, but it's going to be a percent in the bottom. So we have really the years over the percent, and then when you divide by it, you just have a single point. Okay. Now, why does it make sense that our derivative at a is negative for every positive a? Okay, well, what's going on? The number of years it takes for investment to double, if it's compounding continuously, if we're increasing a, what's going to happen? Well, the time to double is going to go down. It's going to keep going down and down and down, and I don't know what the shape of the curve is, but it's going to keep going down as we do it. So if we start here at maybe a 1%, and then if we come over here to 5%, and then we come up here to 9%, or whatever our a value is, the time to double is going to go down. So we should get a negative slope. Now, how this is curved, that's going to be varying, but no matter how we draw our tangents, they're always going to be negative. All right, so let's see, how do we want to write this? Doubling time basically decreases as the percent R increases. Okay, so as we increase this, the time goes down, and therefore, so we get a negative slope. Okay, so that would be what I would say there. Now, we're supposed to write a sentence of interpretation for each of the following statements. All right, so D9 equals 7.7. So what we have here is if we have a 9% interest rate, the compounded compounded continuously, then an investment is going to take 7.7 years to double. So if the interest rate is 9%, it will take 7, sorry. 7.7 years to double. Okay. Now, what does this one say? Well, this one is going to be that instantaneous rate. So 5%, good thing I picked that. And so we're going to get a slope, and that slope is a negative 2.77. So what we can say then, if the interest rate is 5%, the doubling time is decreasing by 2.77 years per percent. Okay, it's give me my 2 per percent. Okay, because we're dividing the percent on the bottom in years, so it's decreasing by that 2.27 years per percent. Okay, now, and that's only at that point. So we can say it's at 5, but it's only going to be for that 1%. And so because we're dividing by whatever percent it is, and then we end up with 1 on the denominator, so it's only from that 5 to 6% really. So that's kind of a key thing, is it's just for that 1%, because maybe by the time we hit 8, it's going to be at a different angle if you think about it, because we're going to divide by different values, so we're going to get a different one. And see here at 12, it's a negative 0.48, and so it's slowed down quite a bit there. Okay, and so the same thing here, if the interest rate is in this case 12%, and it's compounded continuously. So we'll say CC compounded continuously, not Casper College. Then the doubling time is decreasing by 0.48 years until basically that 13. It changes to actually not 13 years, it's 13%. It's going to be, so between 5 and 6 is going to change percent, so 12 to 13% years per percent for 1%. Okay. And then what do we have here? We're back to just a normal D function. And so basically it's just going to be if the interest rate is 16%, compounded continuously again, an investment will double its value in 5.79 years. Okay. And again, there's a lot of writing on these because you have to kind of explain all the things as you go along. And sometimes as you noticed, as 9% compounded continuously, you have to put all that stuff in there to make it actually a valid statement. So sometimes I forget it, but that's something we need to all work on, and trying to get all the little pieces in here that we have. All right, so let's stop there and we'll come back.